Okay, so we have 2 more days of material. This is the differential equations part in this unit, and it's a little extension from what we've done before with differential equations. So some of it will look familiar, however, there's just a little bit of alterations here and there because we're dealing with natural logs and we're dealing with exponential functions. Okay, so this is the all this video is the differential equations, general / particular solutions. In the next video will be your last day, and that last day of video will include slope fields and derivatives of arc or inverse trigonometric functions. Alright, so let's begin. Alright, so differential equations day 1. A differential equation, we know it involves x and y and the derivatives of y. And you could have the first order, so it's like the first derivative, or you could have up to the second order, so a second derivative. So we're going to learn how to solve more general type of differential equations, okay? And they're called variables separable differential equations. And basically, you're trying to separate the variables just like it says. The strategy to solve these is to rewrite the equation so that each variable occurs on only one side of the equation, and it's called separation of variables. So the way we're going to rewrite this is we're trying to get all of one variable on one side. Okay, so only on one side. So you can look at this like dy dx right here is equal to 2x over y. And if you want to interpret multiplying both sides by y, those would cancel. And you would have y dy dx is equal to 2x. Then you would interpret to multiply both sides by dx, so that those dx's cancel. And then you finally get y dy is equal to 2x dx. Now, this is a differential right here, or the derivative itself. And way back when we did the difference quotient, it's the change of y over the change of x. What this separation of variable strategy allows us to do is to interpret those pieces as being multiplied or divided so that we can ultimately get this right here. Again, when I'm solving a differential equation, my goal is to solve for y. I'm trying to get the original function, okay? And it's as a function of x, so it's in terms of x. So my ultimate goal is to get y by itself, so I need to integrate both sides. That way I can get y, a form of y all by itself, so that it's not with its differential of dy. Okay, so the integral of the left side would be y squared over 2 plus, and I'm going to call this one c. Let's call this c1. Okay, and on the right it's going to be x squared, and we'll call this c2. So looking at this again, my goal is to get y all by itself. So I'm going to manipulate some stuff. I'm going to move this c1 over, and it's a form of subtraction. So I could say it like y squared over 2 is equal to x squared plus c2 minus c1. Okay, and all I did was move this c, but I'm paying close attention now to the fact that I'm going to have certain values for these c's. Okay, so I'm going to say y squared over 2 is equal to x squared plus something. Now this right here technically is still a constant, and it's the difference of c2 minus c1, but for right now I'm going to generalize it, and I'm going to call it just c. So at the very end, when I'm trying to get my y by itself, I'll multiply both sides. And the thing is that here's the step that's important. When all the c's are together, okay, you're going to call it just big C. Then as you alter from that, you're going to see the coefficients change a little bit, okay? So multiplying both sides by 2, I'll get y squared is equal to 2x squared plus 2c. And again, I'm compounding onto this c. It is a constant, and yes, now it's multiplied by 2, but no matter what, I'm still compounding onto it. So I'm going to call this c, as more and more gets multiplied, only multiplied onto it, not added, not subtracted, but multiplied onto it. At this point, we're going to keep calling it c. So we'll say y is equal to the plus and minus square root of 2x squared plus c. This is known as the general solution. The reason why it's the general solution is the fact that I don't have c. C is not solved yet. Okay, so it says, your answer is called the general solution. What if you were given the initial condition, y of 1 is equal to negative 3. So y of 1, it's like saying y of x. And what we're doing is we're just going to plug in this 1 value in for x. So whenever I get this 1, I'm going to plug it here, and it will yield a y value of negative 3, which we would have over here. Now, the only one of these two, the plus and minus that you see right here, the only one that's going to yield a negative 3 is the negative itself. Okay, because you can't take the square root of a negative. Okay, so it's not like you're going to have negative times a negative. So we have to set it up as negative 3 is equal to the negative square root of, and again, that's why I know it's going to be negative, because I cannot have any negatives underneath the square root. And then we're just going to plug 1 in. So it's 2, 1 squared plus c. So 2, 1 squared plus c, you're going to get 1 squared is 1, times 2 is 2. So you're going to have negative 3 is equal to negative square root of 2 plus c. From here, if you wanted to square both sides completely, squaring both sides completely, we'll get a positive 9 on the left side, and we'll get a positive 2 plus c. So that when I solve for c, my c is 7. And now that I know c is the c value, I can now form my particular solution instead of it being general. So this general solution that we had right here, is going to become more specific because we now know c. So we'll say y is equal to a negative, not both of them plus or minus. Because we found c and it yielding this negative 3 with this initial condition that was given right here, that's why we're going to go ahead and only have one of them as far as not plus or minus, but just minus right there, and we're going to call it 2x squared plus 7. This is the solution to this differential equation. Again, with this initial condition that was given. Okay, so these are the initial condition problems. Okay, so let's do our next example. So right here, right now, we have dy dx technically is equal to x squared root y. And just like we did the separation of variables on the other side, I'm going to do it here. So try to get y's by itself. Means I'm going to divide both sides by square root of y technically. So, and then also I'm going to do it in one shot. I'm going to multiply both sides by dx. So this cancels, and then it gets moved over here, and then these cancel because the y got moved. So I have like dy over the square root of y is equal to x squared dx. Okay? So what I'm going to do is, again, when I'm solving for y, that's what I'm looking for. I'm looking for the original f of x function, or the y function, for differential equations. I'm going to rewrite this because I'm going to do the integral to both sides. Now you should see right now this y to the negative 1/2 should look familiar. We've done it before. Okay, is equal to, all I did was a rewrite, and then now I can do the reverse power rule as far as I'm going to add a power to the negative 1/2, so I get y to the positive 1/2, then divided by the new power is the same as multiplying by its reciprocal. Okay. And then, of course, I'm still adding, and I can call it C1. Okay, so the right side is going to equal, here we go, x cubed over 3, and then we can call it plus C2. Now, just like we did on the other example, I'm going to move stuff over by dividing both sides by 2, but also moving this C value over. So moving it, I'll get 2y to the 1/2 is equal to x cubed over 3 plus big C. And again, all I did was this C2 minus C1, I've made it into one variable of a constant. And that's what I'm going to continue to do throughout all of these differential equation solving. The next step I would do is divide by 2. So y to the 1/2 is equal to x cubed over 6. And again, it is c over 2, but I'm just going to call it c because it's still the constant. And then right now I'm going to raise both sides to the second power because I'm trying to get y by itself. So it is a square root. If I square both sides, I'm going to get y is equal to all of that thing that you see, x cubed over 6 plus c we can call it squared. And this is the general solution. Okay? So the general solution would be my answer if and only if I was not given an initial condition. So this is an initial condition. This is a point that you're given that you will use to find C, so that you can give the particular, the more detailed, exact answer to the differential equation rather than the general. Okay, so what am I going to do? The input is 3, and then the output 4 is for the y. So when I plug it in, I will get 4 is equal to, again, 3 cubed over 6 plus c quantity squared. Okay? So looking at this, I'm going to get 27 over 6 plus c, and it is squared right now. And again, my goal is to find c. So when I square root both sides, you should remember, anytime you're going to square root and initialize this rational square root, when you initiate it, you're going to give it a positive or a negative always. So then my end result would be plus or minus 2 is equal to 27 over 6 plus c. And of course, if I subtracted that over, it would be a positive 2 minus 27 over 6 and a negative 2 minus 27 over 6. So I'm going to have two c values here. Okay, so let's go ahead and solve them out. The first one, if we get a common denominator of 6, let me get a different color. So it'll be 6, it'll be 12. So 12 minus the 27 is going to be a c is equal to negative 13 over 2. And then making this negative 12 over 6, because again, common denominator, I'm going to get negative 39 over 6. Hold on, I think this is the negative 13 over 2. Negative 39 over 6 is negative 13 over 2. The other one is positive 12 minus 27. So 27, 12, 5, 1, so that's going to be a negative 15. So a negative 15 over 6 would reduce to a negative 5 over 2. So we have a negative 5 over 2 and a negative 13 over 2. So we will have two particular solutions, not just one, but we will have two in this case. We go ahead and write that here at the top. So my two particular solutions become y is equal to x cubed over 6 minus 5 halves squared, or y is equal to x cubed over 6 minus 13 halves squared. Okay? And if you wanted to rewrite that one as far as joining them together, you could say it's x cubed minus 15 over 36 with a common denominator. All I did was just rewrite it a different way, but it's still the same. And this one would rewrite to x cubed minus 39 over 36 all squared. Either one, basically this is the solution, and so is this to the differential equation. These are the particular solutions. Alright, so let's keep going. Our next example has dy over dx is equal to the following, and I do have an initial condition, so I will be using this to solve for c. Okay, so we're going to multiply it by dy dx, so that cancels and we get a dy dx over here. We're going to divide by y squared, both sides, because that cancels, so that we have a rewrite of y to the negative 2 dy is equal to 4x dx. Okay, so here we go. I know that I'm going to integrate these because my goal is to get y all by itself, and right now I don't have it because I have the dy. So when I integrate, it's to get rid of this, and of course the dx as well, so that I only have y's and x's left over. So it'll be y to the negative 1 over negative 1. Again, here I can put plus c, but I'm going to go ahead and skip that step right here because you know ultimately all my constants are piling up on top of each other. Okay, so constant multiple rule that 4 out, so x's antiderivative is x squared over 2. That reduces, that is 2x squared. Now this would be plus c2, and c2 minus c1, I'm just going to call it c. Again, it's just like the other steps, only I'm not doing these c's step by step and writing each individual one, I know that I'm just compounding them, so I'm just going to piece them all together as I go through the problem. Okay, so I have technically right now, let me change this up, negative 1 over y is equal to 2x squared plus c. I can multiply by a negative, so that 1 over y is equal to negative 2x squared minus c. But still, I could still put plus c, it doesn't matter, okay? Because, again, the constants are still compounding on top of each other. We're going to figure those out when we use our initial condition. And then we can simplify this by multiplying both sides by y and dividing by the 2x squared plus c. You can do that, or you can just know that those two will flip. Okay, so all you're doing is multiplying both sides by y and dividing both sides by 2x squared plus c. I'm just going to skip that step because you should be able to do that by now, and I could have negative 1 over 2x squared plus c is equal to y. This is right here, again, the general solution. I will now use this initial value and plug it in accordingly. So the x will go in for the x, and the y will be 3. So I get 3 is equal to negative 1 over 2 times 1 squared plus c. Okay, so it's going to be negative 1 over 2, so negative 1 over 2, or 1 over negative 2 plus c. Let me move this negative, I don't want it confusing you. So we can put it right there. Like here is a negative, but it's the same as I can put it down here if I want. It doesn't matter. I'm still going to get the same answer ultimately. Is equal to 3. And again, the variable is on the bottom, and a constant or whatnot is over here on the top. I can just switch them, and let me write it over here, and have negative 2 plus c is equal to 1 over 3. And then we're just going to add 2 to both sides, so c is equal to 1/3 plus 2. And then adding that with a common denominator is going to be 6 plus 1, so it'd be 7 over 3 is equal to your c value. So plugging it back into my general solution, I'm going to have y is equal to, you can write that negative there, or you can write it down here, negative 2x squared plus 7/3. Alright, so if you wanted to alter this 3 here, you can by getting a common denominator, and if you rewrote it, those of you interested in that practice, you should get this form right here, negative 3 over 6x squared minus 7. Alright, so now let's go to review of proportions. So, if y is directly proportional, so when you see y is, you would write y equals. Directly means to multiply, so it would be k times, and then you're going to multiply by whatever the following variable is, which in this case is t, so you're multiplying by t. So again, directly is the multiplication with k, and the y is proportional is the same as y varies. So when we had direct variation before, back when we were doing like Algebra 2 or Pre-Cal, you were used to seeing y varies directly, directly with t. So y, you would write y. When you saw varies, you used to write equals k. When you saw directly, you would multiply, and then with t, you would just put the t. So that's what this is meaning. It's meaning the same thing. Directly would be multiplication, proportional is that constant with k. Okay? So y is proportional to t is understood to mean directly proportional. So this is where that proportional is, otherwise what we used to call it as varies. So if y is inversely, okay, not directly, but inversely, yes, we will not multiply, we will divide. We're going to have y is proportional, so I'm going to say equals k. That's the same as varies. And then inversely, I'm going to divide by t. And then finally, when you see jointly proportional, you're going to interpret jointly directly proportional. So the default with jointly is directly, and all you're going to do is end up multiplying the two terms that it has with the k value that you're supposed to understand. So y is proportional, that is y equals k. Then when it says jointly, you're going to have more than one piece combined. And again, if it doesn't say inverse, the default is directly. And we know directly is multiplication, so I'm going to have x times 5 minus x. And that's how you would write it. That's just a quick review so that we know how to write things as far as when we read the question. For example, write a differential equation to represent the following. So a certain population P, okay, increases at a rate. So right there, it's not saying P. Because it said the rate, and the rate is associated with P, we're already going to say that is called dp dt. Again, the default with rates is in respect to time, so that's why I have that dp dt there. And then looking at the other pieces, this proportional is like directly, so we know it's going to be k times. And then all we have to do is just bring that variable down, and this is what I read. So dp dt is equal to kt is interpreted mathematically from a population P increases at a rate, so there's that dp dt, proportional, so I'm going to multiply with k to the time t. Okay, let's read the next one. A certain population P increases at a rate, there's another dp dt, and proportional, so it's going to be multiplying with the square root of the population. So we know it's going to multiply with k, but this time it's the square root of P, because that's the population. So all we're doing is we're reading problems and turning them into math expressions or functions. So let P of t represent the number of bears in a population at time t years. So t is greater than or equal to 0 because it's saying that you can't have negative years in this context. So the population P of t is increasing at a rate. So there's that dp dt again. And the reason why I included this t is the fact of how I was given an input variable for this p function. So dp dt is equal to, there's that directly proportional, so it's going to be multiplying with k, and it's this entire piece. So this entire piece is interpreted as what we're multiplying by. So we'll put 800 minus p of t. Okay, and if you wanted to change that up and not have this p of t, some of you are like, oh, that t is going to confuse me. I'll just put it as dp dt is equal to k times 800 minus p. You are more than welcome to. It's meaning the same thing. Just remember that the input for the p function is a t, and that's where you're going to use your initial value problems as far as what pieces are they giving you so that you can solve for the constant c. Alright, so a certain population y increases at a rate, again, that is interpreted as a rate, so it's dy dt. This time it's inversely, so we're not going to multiply onto k, we're going to divide. We're going to take k, we're going to divide by whatever it is that they say afterwards. And what they say afterwards here is the 250 minus y piece. So there would be dy dt is equal to k divided by the quantity 250 minus y. Okay? So let's go on and move to our first example. So, we learned that the differential equation is an equation that involves x, y, and derivatives. We know that the variables that are separable, or with this differential equation, we're trying to separate the variables so that we can find y ultimately after we have found our c value. So, the first order of business is I'm going to divide by y, and the reason, let me tell you something right now. If I divided by 6x squared, I would have 1 over 6x squared, and then I would also have the dx in the denominator. See, I cannot integrate this because the dx is in the denominator. I don't want the dx nor the dy in the denominator. It has to be basically on ground level. That's why I'm moving this y over here by dividing it, so that I have dy over y, which is the same as 1 over y dy. See, there's that ground level interpretation that I'm talking about. That's whenever you can integrate. And again, this rewrite would be y to the negative 1. Now you should see something here, red flagging you as far as this being a negative 1. I can't divide by 0, so this is not going to be a reverse power rule. It's going to be that one that we remember as the natural log of the absolute value of y. Now technically, yes, it is still plus c1. And then on the right side, I still have the dx moved over, and I'm basically integrating 6x squared dx, which yes, the 6 is constant multiple ruled out, and you could say x cubed over 3 times the 6 would give me 2x cubed, and it would be plus c2. Okay, so I'm just showing you the c's because of the fact that this is your first quote-unquote long difficult problem with differential equations. We're going to combine the c's together so that we could rewrite it as the natural log of the absolute value of y is equal to 2x cubed plus big C. Okay, so no more numbers. Just a little review. The reason why I have these with absolute values is because of the fact that y is a variable. Remember, you always want to keep it as absolute value until you're using your bounds or your initial value to find that y, and then see, is it going to be in the domain, or is it going to be undefined because I can't take the natural log of a negative and stuff like that. We've done that before, but right now I'm going to keep it absolute value because of the fact it still is a variable. So what do I do next? Well, I want to get y by itself eventually, so I'm going to basically apply a base of e to both sides. So like all this is the power, all this is a power. We know that these cancel and y is brought down, so that I have e to the 2x cubed plus c. Now, way back when we learned in Algebra 2 that if you have the same base, like 2x times 2 to the y, this would equal 2 to the x plus y. So exponents or exponential expressions with the same base when multiplied, all you're doing is adding their powers. Okay? So looking at this, and again, that is whenever the bases are the same. Like I could have x squared times x to the third. This would be x to the fifth. Okay? So it doesn't necessarily have to be the variable in the power placement. It's just saying whenever you're multiplying things with the same base. Okay? So you see how you got that x to the fifth there because you're adding 2 and 3. So the way we brought these two together, we're going to work backwards to break this apart. So you see that these powers are adding together, and it basically can be rewritten as e to the 2x cubed times e to the c. Because if you were to do this step, going this way, you're going to get e to the 2x cubed plus c. So it's like decomposition, if you will. It's like working backwards. This is still equal to the absolute value of y. Well, why did I do that? Well, the goal of it is to get all my constants together so that I can, again, get a big C going on. So this is big C times e to the 2x cubed. Okay? Now that all the C values are together and they're just like piled on top of each other, I can now use my initial value. Okay? My input for x is 0, so it's like e to the 2 times 0 to the third. We know that's going to be e to the 0, and e to the 0 is 1. Whoops. And then my output value is a negative. So this would change to a negative 5. Okay? And it is an absolute value because all I did was for the y value substitute a negative 5. So I'm going to keep those absolute value pieces, and now you see why I keep those absolute value pieces. Because I can say c times e to the 0 is c, and then over here, this absolute value piece, you're going to see that c is equal to c that, written like that. Okay? Okay, so let's keep going. Now that we have c is equal to the absolute value of 5, or negative 5, we're going to say the absolute value of this is 5, So c is equal to 5. And this is where we're going to check it real quick, because we know the absolute value piece does become a positive 5. Let's check it now with what our particular solution is going to be. Okay, so we kind of went a little bit, glanced over it, but right here is my general solution. The reason it is that I don't know c. And again, my goal is to get to a form of y equals. So I'm going to go here now and I'm going to put y is equal to, the c that I found was 5, and it's e to the 2x cubed. Now, first of all, you can check your answer by plugging in 0 for y. Okay? When I plug in 0 for y, I'm going to get 5 times e to the 0, which is 5. I don't get this negative piece. And this is where the confusing part happens. I have to account for this negative piece because of the fact of it has to work with my initial value. Okay, so the positive 1, even though we have an absolute value here, it could be the positive or negative. We need to check it with our particular solution. Okay, so this is saying that this would be my particular solution because the initial value gave me a negative 5. So it's all about this point right here that I'm talking about that's a little bit tricky when it's in regards to the absolute value of a positive or a negative. You have to check it as far as truly would this positive 5 work, because it's going to be one or the other. It's going to be the positive one or it's going to be the negative one that will ultimately work. Okay, so another thing that you can do is verify that the derivative in fact does yield your original 6x squared times y. Now if you did that, you have a lot of work to do in regards to taking the derivative, but ultimately you don't have to. All you have to do is check, does my initial value condition hold true? Okay, let's do another example. So we have the first derivative. It says that x cannot equal 0 for obvious reasons, because otherwise it would be undefined. I would rewrite so that I could do separation of variables. So dy dx is equal to y plus 3 over x squared. So I would move the x over, the dx that is, and I would move the y over. So it's dy over y plus 3 is equal to 1 over x squared dx. Now they're on the same ground level. Okay, I will integrate both sides. And I could say u is equal to y plus 3. So I have 1 over u, right? 1 over u du, because du is dy. I know it's been a while since we've done u substitution, but this shows that it's going to be the natural log of the absolute value of y plus 3. Okay? So here's something very keen. If the coefficient of y is a positive 1, you can go straight from this to here, okay? Because what you know as far as patterns and whatnot with taking the integrals of these natural log functions, okay? So if it's not a positive 1, then the u substitution does play into it, and you have a little bit more to do. But ultimately, the u substitution is going to work no matter what. I'm just trying to get you a little even faster shortcut so that you can see, yes, this would be the natural log of the absolute value of y plus 3. And yes, there's that absolute value because it's a variable. Technically, yes, it is plus c, but we know by now what we're doing with these c's. I will rewrite this to a negative 2 so that when I integrate it, it becomes x to the negative 1 over a negative 1, and then it'll be plus c. Okay? Now, I'm combining my both side c's into this big one immediately right now. So x to the negative 1, we can't have negative power, so I'm going to rewrite that. It'll be a negative 1 over x to the 1. Now here is where I'm going to start to try to piece on my c's all together. So how do I get rid of natural log? Well, apply the base of e. It's just like here's base level, if you will. So these cancel, and I'm left with y plus 3 absolute value, and then it's e to the negative 1/2 plus c. Again, rewriting this would be e to the c times e to the negative 1/2, because when you multiply things with the same base, you add their powers, and that's what's going on here. We're working backwards again from that Algebra 2 interpretation, because here's big C right there. And this time I chose to write it in front because by now you should see that we're trying to get c e to the negative 1 over x is y plus 3. Okay, so now comes into play again this initial condition. 2 is the input, that will go in for x, and 1 is the output, that will go in for y. So we have y plus 3, so we have 4. And this one doesn't have a negative or positive, so chances are it's just going to be that positive. We don't have to test one or the other to make sure, but we'll still test, and I'll show you how that looks like here in just a bit. So we have c e to the negative 1/2. And again, we're trying to get e to the negative 1/2. Okay? Or sorry, we're trying to get c all by itself. So what I'm going to do is I'm going to divide. So I get 4 divided by e to the negative 1/2. Well, e to the negative 1/2 is the same as e to the positive 1/2 if I move it up to the top. So we can say c is equal to 4e to the positive 1/2. Okay? And if I were to plug that in, because again, where is it at? Right here is my general solution. This is still my general solution, only it's simplified for that c coefficient. And now I can go ahead and apply this c coefficient right there so that I get, let me finish this off. Finish it off in red over here. I'm going to get y plus 3 is equal to, so y plus 3 is equal to this 4e to the 1/2. So 4e to the 1/2 times e to the negative 1 over x. We can add those together and get an e to the 1/2 minus 1 over x with that 4 coefficient. And then yes, at the very end, if we wanted to move the 3 over, we could subtract it. So we got y by itself. Okay. If you choose to put it just as y plus 3, make sure you do leave that absolute value. But here's the thing. You're not going to choose that because of the fact of you need to get y by itself. So how can I check this? Well, this right here is my particular solution. Okay, so 4e to the 1/2 minus 1 over x. Okay, that's a weird power, but that is the entire power right there. And then at the very ground level, it's minus 3. And let's check it. If I plug in a 2, it's e to the 0. And e to the 0 is 1, so 4 minus 3 is equal to 1. Yes, my initial value checked out. So this, in fact, is the correct answer as far as with everything combined and getting y all by itself. Okay, so my particular solution would be the y is equal to 4e to the 1/2 minus 1 over x, and then at the bottom minus 3. Okay, so you should be getting a feel for what is going on by now as far as how we're moving this natural log or the absolute value, how we're double checking the initial value problem as far as what they give us, the initial condition, and so on and so forth. Now let's go on to our first word problem using all this. So the rate at which a puppy gains weight is proportional. So already the weight that is he's gaining is proportional to the difference between the adult weight and the current weight. Okay. And it says at time t is equal to 0, basically when time starts, your initial time, when the puppy is first weighed, its weight is 3 pounds. So if P of t is the weight of the puppy in pounds and t is time in days after the first weight, then your differential equation right there is dt is equal to 1/5 75 minus p. They give it to you. They gave you the initial thing, and yes, it is created from what we read. Okay, so let me read this. The rate, proportional, so proportional, it is going to be multiplication because it was proportional, but that rate right there is dp dt. The proportional piece, there's that multiplication, and it's the difference between its current weight and its adult weight. And they're saying that the adult weight is the 75, so you see the 75 minus p. They're giving it to you as far as the equation itself. Okay, so let y equal your p of t. So if you don't choose to write p of t, you can write y, but it's basically saying the function that you're trying to solve for and find a solution to is p of t. Okay, so you're trying to get p by itself. But we don't just write p is equal to whatever. We want it p in terms of t so that you know what your input variable is. That's what we're trying to do. We're trying to write p of t is equal to something. Okay, and the initial value condition, let me go ahead and highlight that. The point that we will use to solve for c is p of 0 is 3. So x is 0, or sorry, t is 0, that's your input, and 3 would be your output. Okay, and use separation of variables to find p of t, and then the particular solution to the differential equation within the condition p of 0 is equal to 3. So let's go ahead and start solving this differential equation. We know we're going to move the t over, and we're going to move the p over. So the p will be moved over with 75 minus p is divided from both sides. So it's 1 over 75 minus p, and it's going to be dp. The 1/5 stays over there to the right because we didn't need to move it, but we did multiply for, say, the dt over, so it's 1/5 times dt. Now we're going to integrate both sides from separation of variables. On the left, again, the shortcut from what I said from the last screen is that look at that coefficient. That coefficient will tell you, if you don't want to use u substitution, what it will be as far as the antiderivative. So this is a natural log because you have 1 over the stuff. So it'd be the natural log of 75 minus p in the absolute value. And because of this negative, if you chose to do u substitution, you would end up multiplying by a negative. So it's negative natural log of 75 minus p. Now, if you want to, you can do the work with u substitution. I'm showing you the shortcut because I want you to be fast at this. These will be the free response questions, one of them of the 6 that you'll do on the AP exam. I want you to be fast. This is why I'm showing you the tricks of the trade as far as the coefficient there. So 1/5 dt becomes 1/5 t plus c. Now again, I know I have a c on this side, had a c on this side, but I chose to only write it once because I know by now that I'm combining it to a big C at this point. And then now I can start solving for y, or trying to get, not y, but p, okay? Because you know y is equal to p of t. My goal is to get this p all by itself, okay? So from here I'm going to multiply both sides by a negative. So I get natural log of 75 minus p, absolute value that is. And then I'll get a negative 1/5 t. Now it's minus c, but again, it doesn't matter. We could just put plus c all day because we're going to find what that variable is here at the end. I will apply now a base of e to both sides because my goal is to cancel that so that I can drop that 75 minus p. Again, I'm trying to get p all by itself. So I'll say the absolute value of 75 minus p is equal to e to the negative 1/5 t plus c. And yes, this is the same as e to the negative 1/5 t times e to the c, from what we talked about from that algebra 2 stuff as far as multiplying with the same base, we add the powers. So I can combine these together. Whoops. I can combine those together to get c. I'm going to go ahead and write that right now. Okay, so I'm going to combine those together, and I'm going to get big C times e to the negative 1/5 t. So we're almost there. Okay, so technically this is my general solution right now because of the fact that I have not yet found C, but it's pretty much almost all, like you don't have to get P completely by itself in order to solve for C. Okay, I choose to do that, but you don't have to. From this point, what I would do is try to solve for C. So what I'm going to do is I'm going to plug in my initial condition of t is equal to 0. So that 0 would go right there. So you have e to the 0, so that's 1. And then you plug in 3 for p. 75 minus 3 is 72. The absolute value of that, again, because it's positive, I don't really have to interpret, could it be the positive or could it be the negative? It's only when it's negative in there, it might be one or the other. You have to check both. But when it's a positive, I can assume c is 72. And now I'm going to plug it back into the original equation. So that I have 75 minus p. I get the absolute value of 72 is 72. So I don't need that absolute value there anymore. And I can say 72 e to the negative 1/5 t. So negative 1/5 t. Alright, so looking at this, the only thing that I have to do at the very end is get p by itself. So I'm going to move stuff over. I'm going to subtract. So I'm going to take this off, and I can lift it off right now because it was a positive interpretation. So rewriting it, so let me take that off. 75 minus p. And then I can move over the p to the right if I want and subtract all this so that I get 75 minus 72 e to the negative 1/5 t is equal to p, or p of t. Now, the only thing we have to do, again, just for good measure, is double check this. If I put 0 here, I would get 3 as an output answer. So we are good. Okay, so we are almost done. A couple more problems. Let's solve for y on this differential equation. Okay, just like what we've been doing, we're trying to get y all by itself. We're going to do the separation of variables, and then we're going to plug in our piece. Now, already you see y by itself is going to be a little bit weird as far as to moving it over to the left side. So how are we going to move this piece when our goal is to get y by itself? Okay. Well, you see that you have 4x cubed. You can GCF out from y plus 3, because if you were redistributing this, you would get its original differential equation. Okay, so 4x cubed y plus 12x cubed. From here, now you have y by itself. So we can move it over by dividing by y plus 3. There's that dy on ground level. Then we have 4x cubed. Multiplying that dx, there's that dx on ground level. And now, the natural log of the absolute value of y plus 3, it will not multiply by a negative right there, so I'm going to take that off because of the fact that this coefficient is a positive 1. All it is natural log of y plus 3. And again, it's only because it's a positive 1. If it was a positive 2, you would have to do u substitution. If it's anything other than positive 2 or positive 1, you have to do u substitution. The only thing is that I would say if it was a negative 1, you could do that shortcut as far as accounting it for a negative right there. Okay. Okay, so there's the left side. When I do the right side, I'll get, well, x to the 4th over 4. That cancels, so you have x to the 4th plus c. Okay? And again, we're trying to get y by itself. So I'm going to apply e as the base. Those cancel, and you get y plus 3 is equal to, by now you know you have e to the x to the 4th times e to the c. E to the c is big C times e to the x to the 4th. And now you're just going to use your initial value. This is your x value, and this would be your y value. So negative 5 plus 3 is a negative 2. There's that negative, so we have to, because it's a negative inside of this absolute value, we're going to have to think, it might be the positive, it might be the negative. We have to maybe try both. So y is equal to 1, so we have c times, not y is equal to 1, x is equal to 1. So we have this. So if I divided this out, I could say negative 2 over e to the 4th. Okay? Negative 2 over, see, this doesn't have a negative power to it, so I don't have to move this e to the negative 4 up. Okay? I can just leave it where it's at because it's technically written as a positive power right now. And this would be c. So it's either this or it'll be the 2, positive 2, e to the 4th. Okay? We'll look at my initial value to see which one it is. Okay? So if I looked at the particular or the general solution and I plug in one or the other, let's say that I plug in c is equal to negative 2 over e to the fourth. Okay, so if I plug this in here, I would get negative 2 over e to the fourth times e to the x to the fourth. Okay, looking at this, I can move this up by saying it's negative 2 times e to the negative 4 times e to the x to the fourth. Why would I do that? Because I'm trying to combine these e's so that it looks a little bit cleaner. X to the fourth minus 4, because you're adding them. There's that negative 2 coefficient that came from my value of c, and it's equal to y plus 3. Now we can just check our variables. So if I plugged in 1 for x, I would get 1 to the fourth is 1 minus 4 is negative 3. So I'd get negative 2 e to the negative 3 is equal to, and then I get negative 5 plugged in for y plus 3. I'd get negative 2, and the absolute value of that wouldn't equal this negative 2. Well, the absolute value of negative 2 is 2. It would not equal what this is over here. Over here I have a negative 2 over e to the third. Those are not the same, so it's probably not going to be that negative piece. It's probably going to work out with the positive. So let's go ahead and do that with the positive. Let me get rid of all this so that you're not confused with it. Okay? So this one didn't work out as far as our initial condition. So it's probably going to be this positive 2 over e to the fourth. Okay? So plugging this c value into my general, I'll get y plus 3. I'll get 2 over e to the fourth times e to the x to the fourth. Moving this around, I get 2 e to the negative 4 times e to the x to the fourth. And then I get x to the fourth minus 4. Oops, not like that. X to the fourth minus 4 is the power of e. And then you get y plus 3. Okay, so now if we put 1 in, do we get the negative 5 piece? Okay, so if I put this 1 in, I'm going to get 1 to the fourth is 1 minus that would be a negative 3. So 2e to the negative 3 is equal to negative 5 plus 3. So that's a negative 2. And would this in fact equal that? So does the absolute value of that, would it in fact equal it? Okay, so I caught my mistake. Whenever I was looking at the initial, the general solution, so probably people are trying to think about emailing right now, the y plus 3, when I first plugged in this negative 5 and I got a negative 2, and I plugged in 1, I should have had c times e, not c times e to the fourth, because 1 to the fourth would have been 1. So then I would have negative 2 over e was c, or a positive 2 over e was c. Okay? So one of these checks out. That makes a lot better sense. Okay? So looking at this, let's go to checking them both out. So I shouldn't have had a power of 4 on that e base. Okay? So this is my general. Plugging it in as far as c is equal to 2 over e. You would have 2 over e times e to the x to the fourth is equal to y plus 3. This would be rewritten as e to the negative 1, e to the x to the fourth. You're multiplying them, you have y plus 3. And then this would be x to the fourth minus, x to the fourth minus 1 is the power of e. 2 is a coefficient, and you have something like that. So now if I plugged in negative 5, okay, negative 5 plus 3 is that negative 2 piece. And then if I plugged in the 1, I'd get 2 here. So the absolute value of 2, or negative 2, would equal that positive 2. So in fact, this one does work right here. Okay, let's make sure that the other one doesn't work. So if I go and I plug in the other 1 instead of positive 2 over e? What if I put a negative 1 right here, or a negative 2 over e? So this would be a negative, this would be a negative, this would be a negative, and this would be a negative. And the absolute value of negative 2 is not going to equal to negative 2. That's why this one doesn't work. So you can write your final answer as y plus 3 absolute value is equal to 2 over e times e to the x to the fourth, which is better rewritten as 2e to the negative 1 times e to the x to the fourth is equal to the y plus 3, so that ultimately it's 2e to the x to the fourth, and it's minus 1 is equal to y plus 3. You can write it like that if you want. If you want to move it over and subtract the 3 thereafter, you can do that as well. Let me make sure on that. Negative 5, negative 2 is 2. No, you could leave it like that. You could leave it like that. Don't move it over from that interpretation. This would be your final answer, and you would get full credit. That's a particular solution. Okay, so that's where we're going to end. So your last video will have a little bit more of particular solutions and general solutions with differential equations, just a little bit more practice with other word problems. We'll look at some that have incorporated the second derivative. And then finally, we'll have slope fields and the inverse trigonometric functions on that as well, that video. And then that's it. It's just review from there on out.